back to math and modeling methods. And today would be lecture number 21. Okay, so we've been talking about separation of variables and superposition for steady problems, and in particular we've been concentrating on the Laplace equation or the Poisson equation. So any engineering or science problem that's governed by that equation, which in our case, heat transfer problems, mass transfer problems, or fluid mechanics problems, ideal fluid mechanics problems in this case, could be potentially governed by that particular equation. Now, starting today, we're going to be looking at transient problems and see how can we deal with those and how we deal with partial differential equations where the time is involved, and see if we can apply separation of variables directly, or if we need any special kind of tricks to be able to apply it. And we're going to apply these to different types of equations, diffusion equation, and also some wave-like equations for vibrations, and see how they come about. And then starting next week, we're going to try to do whatever we're doing for partial differential equations, we're going to try to do it numerically, and see if we can come up with a scheme to approximate the solution, a general scheme, and then compare it to some of our analytic solutions. All right, so how do we deal with time-dependent problems? Time-dependent, or what we call transient problems. And those are usually encapsulated into a class called initial value problems. All problems that depend on time need some sort of initial condition, or at least one initial condition, depending on the nature of the problem. So, separation of variables may be used if, and only if, we have a homogeneous, all initial requirements apply. The problem needs to be linear. The problem needs to be framed in an orthogonal coordinate system, so it needs to be in a square, rectangle. Later, when we deal with cylindrical coordinate system, it has to be a cylinder or a hollow cylinder. We cannot escape that. So we have to have homogeneous governing equation, essentially no generation or forcing of any kind in the governing equation. We have to have homogeneous boundary conditions. They all need to be homogeneous, whatever kind they are. They can be first kind, second kind, or third kind, but they need to be equal to 0, all of them. And the only thing that we can deal with that's non-homogeneous is an initial condition. So the entire problem, well, that's not a requirement for the problem. The problem can be anything it likes to be. But in order to be able to use separation of variable, the problem needs to be driven by the initial condition. This is the only thing that is going to keep it out of 0. Okay? So it's basically we're looking at a diffusion problem where the problem will start at a level. Either that level is constant or it's a function itself of space at time equals 0. And then the problem will decay or equilibrate to whatever the boundary conditions are telling it to equilibrate. And all of these are homogeneous. All right, so let's go straight to an example and see how we implement this, because nothing's going to be new. We're going to do eigenvalue decomposition or eigenvalue expansion, and essentially the same. So let's look at a 1D transient heat conduction, also called transient heat conduction, is also known as heat diffusion. Same thing. All right, so diffusive-like problems are governed by an equation that has a first-order derivative in time. Okay, which, if you remember, anytime we have a first-order derivative in time, the solution in time would look like an exponential, like a decaying exponential, right? So that's the nature of diffusion problems. Diffusion problems will not oscillate in time. It will not be a vibration type of problem. Diffusion problems will actually tend to equilibrate over time because of their nature. A first-order derivative in time leads to an exponential, a decaying exponential in time. So, in the case of 1D transient heat conduction, we have the governing equation looking like this. We have the derivative, or the second derivative of temperature, and let's see Since we're talking about 1D, we're going to add it there, is equal to 1 over alpha dt dt. And we call this diffusion equation. By the way, any problem that is governed by that equation is known as a diffusion type problem. And there are many, not only heat transfer or heat conduction in this case. That quantity alpha is equal to the conductivity divided by the density divided by the specific heat capacity at constant pressure, which for solids is just the same. Cp and Cv are the same, if you remember. This is the units of these. If you take the units of K, watts per meter Kelvin, the unit of density being kilograms per meter cubed, and the units of Cp being joule per kilogram Kelvin, you end up with meters squares per second. Meters squares per second. Any type of diffusion equation, whether it is energy diffusion in this case, or heat diffusion, or it is mass diffusion, or it's fluids diffusion, whatever it is, has a diffusion coefficient. This is called the thermal diffusion coefficient or heat diffusivity. So whether you're talking about mass diffusion, I don't know if you ever saw this in heat transfer, there's a section in which you talk about species diffusivity, how different species diffuse into another species, talking about chemical species. And whatever you talk, you caught that, huh? Yeah. So whatever you're talking about in terms of whatever variable is being diffused, there's a diffusion coefficient that carries exactly the same units. Because as you can see here in this case, the temperature cancels out with the temperature, and all you're left with, oh my bad here, this should be x squared. My bad, yeah. You have space squared over time. That's what the diffusivity coefficient. So in the case of mass diffusion, it's called D. In the case of momentum diffusivity in fluids, it's called nu, or sometimes called kinematic viscosity. That also has a unit of meters squared per second. Okay? So let's say that we have an initial condition that looks like, since the problem is first order in time, there's only one needed initial condition. So only one allowed initial condition. And we're going to call that f of x. And then we have boundary conditions. Let's say that we have dt dx at x equals 0 is equal 0. That's homogeneous. So that's second kind. Homogeneous. And this is also implying that the problem is insulated at x equals 0. Q is equal to 0, translates into dt dx equals 0. And let's say on the right hand side we have dt dx at x equal L plus h times t at x equal L is equal to 0. So that's a third kind, homogeneous as well. And that means that we have convection with h equals h over k and t infinity equals 0. That's what that convection condition looks like on the right hand side, and it just basically translates to that. We already went through the denomination of the types of boundary conditions and how do they translate into either first derivatives or the value of the function in the case of first kind conditions. Alright, so how do we deal with this problem? Since all the conditions apply, the governing equation is homogeneous, the boundary conditions are homogeneous, and the initial condition is non-homogeneous, and we obviously have a linear separable problem, SOV applies directly. That means that we're going to let t of x and y, t of x and t, equal to some function of space x times some function of time tau. Same thing we did with x and y, now we're going to do with x and t. Now, however, there's going to be less ambiguity on the part of trying to select the sign for the separation constant because the sign is going to come out naturally. So this one technically is a bit simpler. So plug in into governing equation leads to the following. It leads to x double prime of x times tau of tau equals 1 over alpha x of x tau prime of tau. Single derivative in time, double derivative in space. Now we can separate by dividing everything by x and tau. We get x double prime of x divided by x of x equals to 1 over alpha tau prime of t divided by tau of t. All right? So we've arrived at a separated expression where things on the left are a function of x only, things on the right are a function of x only, and therefore this can be separated. The only way that they can be equal to each other is if they're both equal to a constant. And we're going to make that constant negative all the time. Now, because as this is a diffusion problem, notice the equation in time. Always negative. If we look at the equation in time, we're going to end up with tau prime of t plus lambda squared, or alpha lambda squared tau of t equals 0. And that leads to a solution e minus alpha lambda squared t. We need that minus sign because the solution in time has to be decaying. Okay, it has to lead to an asymptotic solution, it has to lead to equilibrium. Have we selected a positive sign here? Well, not only we'll have a positive exponential, which is a solution that grows forever, but we would also have none an eigenvalue problem in the x direction. We need that negative sign because we need that negative exponential, need negative exponential. And at the same time, that negative sign is necessary to form an eigenvalue problem in the x direction. So when we go to the x direction, we're going to get x double prime of x plus lambda squared x of x is equal to 0, subject to homogeneous conditions. If we look at the original conditions, the conditions are both homogeneous, therefore they're separable, and we're going to get x prime at 0 is equal to 0, and then we're going to get x prime at L plus h times x at L is equal to 0. Those are the two conditions. All right? So we can go to the table that I posted on Canvas and check out what case is that for an eigenvalue problem. What combination case? Remember, we have 9 possible combinations of boundary conditions. Do you happen to have the table with you or access to the table? If you look it up, that will be case number, I can't remember. But let me see if I printed it out. But anyways, I'm going to write it here for you. If you check it out while I write this, case number such in table. So we get eigenfunctions, cosine of lambda n x, such that the eigenvalues roots of this equation. So these are the eigenvalues, eigenfunctions. And 1 over n of lambda n, that's the other thing that we can recover from that table. Is exactly twice h squared plus lambda n squared divided by L h squared plus lambda n squared plus h. That's a result of applying orthogonality. That's essentially the integral of the square of this eigenfunction between 0 and L, where the eigenvalues are these. That leads to that. You can try it. That's what you're going to get. What case it is? There's 9 cases. Resources. There you go. And there's one rectangular, another one. Probably the first one. It's probably cylindrical. By vertical. Yeah. No, that's it. Yeah. Okay. Second. Solid cylinder. Rectangular was before solid cylinder. Right. So when we have second kind on the left and third kind on the right, that would be case number 4. Case number 4 on the table. And can you confirm that these are indeed the eigenfunctions, eigenvalues, and inverse of the norm? Yeah. All right. Okay. So then we put it all together. And essentially, the temperature from x and t is equal to the summation from n equals 1 to infinity of Cn cosine of lambda nx e to the minus alpha lambda n squared t. So now in space we have cosines, so oscillative functions of different frequency that when added together, they form a flat function or whatever they're trying to converge to, according to Fourier. And in time, you end up with exponentials of different decay. Lambda n, remember, actually decreases or increases in time, and increases as a function of n. So you have much faster decay of the exponential added to the different frequencies of, or multiplied to the different frequencies of trigonometric functions. So this is again the general solution. And then apply initial condition, which says that t of x and 0, we were given some function f of x which is known, is equal to, and it comes out actually simpler than the steady problems, because when time is equal to 0, the exponential goes away regardless of what the frequency of the, or what the decay of the exponential is. It just comes out to 0 at time equals 0. Using orthogonality, then we have that the integral from 0 to L of f of x cosine of lambda n x dx is equal to Cn times the integral from 0 to L of the cosine square of lambda n x dx. Oops. We have already used orthogonality. That's why we get rid of the summation. And therefore, Cn is equal to the integral from 0 to L of whatever the initial condition is times the cosine of lambda n x dx divided by which this one right here is that norm of lambda n. And that's why the table shows you the inverse of the norm, because it always goes into the denominator. So Cn, for completeness, is h squared plus lambda n squared divided by L h squared plus lambda n squared plus h times the integral from 0 to L of f of x cosine of lambda n x dx. Now the problem is solved. Recall that the tangent of lambda n L is equal to h over lambda n, and that's how we get the eigenvalues. The roots of that function, which if you remember, those are an infinite number of roots, but they're not uniformly spaced, okay? Because it's the intersection of the tangent function with 1 over lambda n function, with an asymptotic function. And so they actually intersect every pi, or pi half, but not regularly. All right. Now, this is very easy to implement, as you can see. What do you do if you have multi-dimensions? Same thing, same idea. So let's say that you have multi-dimensional transient problem. Let's say again that we're dealing with heat conduction or heat diffusion. So let's say that we have x, y, z, and t is equal to 1 over alpha dt of x, y, z, and t. Where Laplace is a space operator, and on the right hand side you have the first order derivative. Let's say again that the initial condition at time equals 0 is given by some function which is known, provided. And let's say boundary conditions homogeneous on all phases. Whatever they are, first, second, or third kind, they're homogeneous in all cases. Okay, so what do? Same thing. Let t of x, y, z, and t. And in the initial step, we're not going to break it up into x, y, z, and t functions. We're going to break it up into a space function, x, y, z, times a temporal function. So that psi is a function that only holds space information, and tau is a function that only holds time information. So back into governing equation, we get tau of t times the Laplace of psi of x, y, and z is equal to 1 over alpha psi of x, y, and z times tau prime of t. Furthermore, this will be Laplace of psi of x, y, and z divided by psi of x, y, and z equals to 1 over alpha tau prime of tau divided by tau of t. That's the new governing equation. And again, the governing equation shows a function of space on the left and a function of time on the right. The only way that they can be equal to each other is by both being a constant, and we're going to pick that constant to be negative for the same reasons that we've been saying. So in the t direction, we have tau prime of t plus alpha lambda squared tau of t equals 0, leading to tau of t equals to a times alpha minus alpha, or e to the minus alpha lambda squared t. That is the solution of that equation. All right. Now in space, we have x, y, z, leading to an equation that looks like Laplace of psi of x, y, and z, and plus lambda squared psi of x, y, and z is equal to 0. Now we have a partial differential equation, because this is an equation of x, y, and z. We have a partial differential equation. It's linear, homogeneous, but it's not the Laplace equation, it's not the Poisson equation, because we have that extra psi here. This is called the Helmholtz equation. And the Helmholtz equation in this particular case is a consequence of applying separation of variables in space and time. But the Helmholtz equation on its own governs a family of other types of problems in mechanics, such as acoustics. If you want to know how an acoustic field propagates in a medium in the frequency domain, not in the time domain, it is through the Helmholtz equation. Okay? So other phenomena also are governed through the Helmholtz equation. But for us, all we need to do is solve it so that we can end up with a temperature. In order to solve it, we're going to do the usual. Let that function of space be equal to a function of x, a function of y, and a function of z. And therefore, the governing equation, the Helmholtz equation, will look like x double prime y z plus x y double prime z plus x y c double prime. That's the Laplace. Plus lambda square x y z is equal to 0. That's how the equation looks like. Then we can divide the whole thing by x, y, z. And that will be x double prime of x divided by x of x plus y double prime of y divided by y of y plus c double prime of z divided by z of z plus lambda square is equal to 0. Need eigenvalue problems in all directions. Since we remember we have homogeneous boundary conditions everywhere in all phases. That's a requirement for the application of separation of variables. So now we can separate these x double prime of x of x is equal to minus y double prime of y over y of y minus c double prime of z of z minus lambda square, and then we make that equal to constant beta square, which will make negative 2 because we need an eigenvalue problem in the x direction. So in the x direction, we have x double prime of x plus beta square of x is equal to 0, plus homogeneous BC's in the x direction, leading to x of x beta n's, and n of beta n's. Eigenfunctions, eigenvalues, and norm. That's what we get out of these. We just go to the table with a combination of homogeneous equations or homogeneous conditions and get whatever eigenfunction, sine, cosine, or combination thereof. All right, so now we have x. We have tau, we have x. We need to get y and z. Same idea. What do we have so far? Back to the governing equation, we have minus y double prime of y divided by y of y, minus c double prime of z, c of z, minus lambda square is equal to minus beta square. Now we isolate y of y, and that's equal to minus c double prime of c, c of z, minus lambda square, plus beta n squared. And now we have y's on one side, z's on the other side. This can only be equal to a constant. We're going to call that constant gamma squared. And we're going to make it negative again because we need an eigenvalue problem in the y direction. Same idea. So y is going to be y double prime of y plus lambda or gamma square y of y is equal to 0 plus some homogeneous DCs. That would lead to y of y, gamma m's, and n of gamma m, again eigenfunctions, eigenvalues, and norm. Okay, so now we're only missing z, which is this one. So we have minus c double prime of z divided by z of z minus lambda square plus beta n square is equal to minus gamma m square. So that's pretty straightforward. We can say that z over z.
Shouldn't it be plus gamma n squared?
Huh? Is equal to.
Oh, sorry.
Minus lambda square plus beta n square plus gamma m square, and we're going to make this equal to delta square, and we're going to make it negative again. Sorry, this is equal. Yeah. And we're going to make it equal to minus delta. And again, that would lead to a problem in the z direction where we have c double prime of z plus delta square of c is equal to 0 plus some homogeneous conditions. And that would lead to z of z, delta, and this delta is going to be with a separate index, L. And then some norms of delta L's, eigenfunctions, eigenvalues, and norms. And then we put it all together. That's how we construct a solution. then t of x, y, z, and t is equal to the summation from n equal 1 to infinity, the summation from m equal 1 to infinity, over the summation from L equal 1 to infinity of Cn ml times whatever these eigenfunction in the x direction is, whatever the eigenfunction in the y direction is, whatever the eigenfunction in the z direction is, times e to the minus alpha lambda square t, by the way that lambda depends on n, m, and l. Such that from here you can see very clearly that lambda square of n, m, l is equal to beta n square plus gamma m square plus delta l square. So it all comes together. And through orthogonality, we can find CNML is equal to the integral. Alright. Integral from in the x direction, integral in the y direction, integral in the z direction, whatever the limits of those are, of the initial condition, times these eigenfunctions, dz, dy, dx, times 1 divided by the norm of beta n, the norm of gamma m, and the norm of delta L. Yeah. And all of that to make a very simple problem in a parallelepiped, because this only works on parallelepipes. It only works when the geometry is framed in a coordinate system that's orthogonal. In the case of Cartesians, it has to be a parallelepiped, not even a hollow parallelepiped. It should be a cube or an elongated cube. And it has to be homogeneous everywhere except on the initial condition. So the most simple kind of problem leads to this nasty looking series expansion as 3 embedded summations. But it's the only way, so far, that we can get an analytical solution to a well-posed problem. And it would be the only way that we could actually validate whether a numerical solution is valid or not, knowing whether to compare it to something mathematical. That's the basis. Well, starting next week, we're going to learn how to solve these problems numerically. Now, using a basic finite differencing approximation, there's obviously much more to that. The class next semester will be about how to solve these problems numerically through many different techniques. But over the next week or so, we're going to be talking about finite differencing as the first approach. It's the oldest numerical methods that exist to solve either boundary value problems or initial value problems in multi-dimensions. All right. Now, what do we do when we have non-homogeneities? Okay. What if non-homogeneities exist in governing equation and or boundary conditions? Then we can apply superposition and separation of variables as long as non-homogeneities are not time dependent. if non-homogeneities are time dependent, then we must use different methods such as variation of parameters, or Green's functions. Okay, and both of those I'm going to skip. Okay, last semester I went through some introduction of those, but we're going to have time to do that this semester with the time change. Well, these are just other analytical techniques that depend or rely on eigenvalue expansions. The same thing, you end up with series summations, and the series summations are of eigenfunctions. At the end of the day, the final form of the solution looks the same, but it's just additional methods. All right, so let's go through an example. What would happen if we have, so let's say 1D heat diffusion with generation. So let's say that the governing equation is the second t dx squared, and again we're talking about, let's see, a 1D problem in time, plus u g triple prime divided by k is equal to 1 over alpha dt dt and x and t. Okay, so now we have a generation term, which can also be called a forcing term. It's just basically a non-homogeneity, and we're assuming that it's a constant. It's not a function of time. It cannot be a function of time. I mean, it can be a function of time, but if it is, we cannot apply superposition and separation of variable. Let's say that the initial condition is t of x and 0 equals to some given function of x, f of x.
Should be a function of space.
Hmm?
Can it be a function of space?
What's that?
Your heat generation function.
It can be a function of space, yes, but it cannot be a function of time. And let's say that the boundary conditions are, let's say the t dx at x equals 0 is equal to some a, and let's say that t at x equal L is equal to some b. Okay, well, this comes from saying that the q at x equals 0 is equal to q0, which is equal to minus k dt dn, minus k dt dx, times at x equals 0 times minus 1. So therefore that a is equal to q0 divided by k. All right? So what do? We're going to use superposition. And when you're talking about transient superposition, what you do is say the t of x and t is going to be a transient function, which we're going to call t1, plus a steady function that we're going to call t2. That is a superposition that we're going to try. Notice T2 is the equilibrium steady state or asymptotic solution. That's what would happen when time goes to infinity. This one will vanish, and you'll be left with T2. That's what would happen if the problem was steady state. If the time dependency didn't exist, you're given this set of boundary conditions right here. The equation is perfectly steady. T2 will be the solution that you will arrive at. So this is basically a superposition between a transient and an asymptotic solution. If you go back to governing equation, you end up with the second derivative of T1 with respect to x squared plus the second derivative of T2 with respect to x squared, which is a total derivative because T2 only depends on space, plus UG triple prime over K is equal to 1 over alpha d T1 dt. And now we're going to separate into, well, we're going to let the second T1, the x squared, equals to 1 over alpha dt1 dt. And therefore, the second T2, the x squared, plus UG triple prime over K is equal to 0. So we pass on the non-homogeneity, UG triple prime over K, over to the steady solution. And let's see how this breaks up. We have initial condition and boundary conditions. Let's start with the boundary conditions. We're going to keep the boundary conditions of the T1 problem homogeneous. We got to keep them the same kind as the original boundary conditions. So that the boundary conditions for the T2 problem look like dt2 over dx at x equals 0 is equal to A, and T2 at x equal L is equal to B. Is that clear? Same thing we did before with superposition. Since T1 plus T2 is equal to T, the sum of the boundary conditions also have to match the boundary conditions for T. How about the initial condition? What is the initial condition T1 at x comma 0? That would have been whatever the initial condition for Tx was minus T2x. So it would be equal to f of x minus T2 of x. So we need to find T2 in order to solve for T1. Alright, so the T2 problem looks like the second T2, the x squared, plus UG triple prime over K, which is a constant, or we are given a constant. It can also be a function of space, as you mentioned, but it would just be a matter of integrating it twice and finding its solution. Subject to the T2, the x at x equals 0 is equal to A, and T2 at x equal L is equal to B. So when we integrate this twice, the solution T2 of x is equal to minus UG triple prime over K times x squared over 2 minus L squared over 2 plus A times x minus L plus B. Remember, A and B are given. They are the boundary conditions, original non-homogeneous boundary conditions. These are not constants of integrations, have already been incorporated into this expression. So this expression satisfies this equation, and it satisfies this boundary conditions. If you differentiate it and evaluate x equals 0, you get A, and if you evaluate it at x equals L, you get B. All right, so now we need to solve for T1. The T1 problem, we have one over alpha dt1 dt such that T1 at x comma 0 is equal to f of x minus t2 of x, and the boundary conditions say that dt1 dx at x equals 0 is equal to 0, t1 at x equals L is equal to 0. These are homogeneous. This is second kind, first kind, homogeneous. So we go through the solution process. T1 of x comma t will be the summation from n equals 0 to infinity of Cn cosine of lambda n x e to the minus alpha lambda n squared t. Such that lambda n is equal to pi over 2L times 2n plus 1. Those are the eigenvalues. So that would be, I think that's case number 6 on the table. The norm of lambda n is L over 2. The inverse of the norm is 2 over L. And therefore Cn is equal to 2 over L times the integral from 0 to L of f of x minus t2 of x cosine of lambda n x dx. And at the end of the day, what we're looking for is simply t1 plus t2. And that's the answer. So that's how we apply superposition in the case of transient problems. We always superimpose a fully transient solution with all dependencies, space and time, plus an asymptotic solution, which will be the solution in only space. T2 would be the solution that this series expansion will take, or the solution that the problem will take when time is equal to infinity. That's a steady state solution of the problem. All right. So what do we do in other types of problems? We've been discussing heat conduction, which is governed in steady state by either the Laplace equation or the Poisson equation if there's generation, and in time it's just the diffusion equation. We mentioned that that equation also applies to many field problems, not only heat conduction or heat diffusion. It can be mass diffusion, it can be ideal fluid flow, it's governed by the Laplace equation of the stream function or the potential function. Many things are governed by Laplace equation, Poisson equation, or the transient version of these diffusion equation. But how about problems in acoustics and vibrations or in electromagnetics? There's always that second derivative in time. There's always that wave-like behavior that leads to waves. So let's see how we deal with that and see if we can actually implement separation of variables in that case. wave-like problems. And those are, well, we have acoustics. That would be acoustics in the time domain. We mentioned that acoustics in the frequency domain is governed by the Helmholtz equation. Vibrations, electromagnetics, etc. So back at the beginning of the semester when we were talking about field theory, Laplace, curls, and so on and so forth, we talked about the Maxwell equations. Notice the Maxwell's equations have second order derivatives in time. So, for example, typical equation of vibrations. This is called the wave equation. Where, by the way, that x can be x, y, and z. It's just space. All right? So now we have the speed of propagation of the wave, which, for example, in electromagnetics will be the speed of sound. For example, if this is the vibration of a membrane, right? Let's say a membrane that is constrained all the way around, then C will be related to the modulus of elasticity of that membrane. So the stiffer the membrane, the faster the wave will propagate, right? And eta would be just the amplitude of the wave, okay? The position of the membrane with respect to a datum at any time, or Z, okay? Also, we can have another kind of equation that is wave-like, that looks like this. So notice now we have a first and a second derivative in time, and this is what's known as the damped wave equation. There's some damping effect induced by that beta, which can be either a viscosity, a damping, a dashpot coefficient, anything of that nature. All right. How do we deal with these? Let's go straight to an example where we say, let's say we have a square membrane. Eta equals 0, eta equals 0, eta equals 0, and eta equals 0. So this is a clamped membrane such that eta is a deformation in space and time. So think of a drum. Well, in the case of a drum, we have a circular one, so we'll have to use polar coordinate systems. But think of a square drum. Okay, you clamp it, and then depending on the characteristics of the material of which the drum is made of, the membrane is made of, it will vibrate at different frequencies and will produce a certain sound. Okay? In the case, the eta is a deformation, essentially meaning the position with respect to a datum or a reference line as a function of time and space. It's 0 on the borders because it's clamped completely. So the governing equation for these, as expected, c squared times the second eta dx squared plus the second eta dz dy squared, so mean that this is x and this is y, equals to the second eta dt squared, and this is function of x, y, and t. The initial condition, since the problem is, as you can see, second order in time, we need two initial conditions. We need the position at time equals 0, and let's say that that's some given function f of x and y. which can be 0. Okay, let's say that the membrane is originally at rest and is completely parallel to the line of reference. And let's say that the initial speed is some other function gxy. So let's assume that this is a drum clamped on the periphery, and let's say that the original state is 0 stationary, but then we perturb it with an initial speed. Or we can perturb it with an initial position. We can just hit it in the metal or pull the metal, raise up eta for the deformation to a positive value, and see how it would vibrate. And the boundary conditions, we have eta of x, y, and t at all portions of the boundary equal to 0. So we have homogeneous boundary conditions. So because we have homogeneous governing equation, homogeneous boundary conditions, and non-homogeneous initial conditions, doesn't matter that there are two non-homogeneous initial conditions, separation of variables applies directly. So we're going to let eta of x, y, and t be equal to some function w of xy times some function tau of t. Separated into space and time like we do with multidimensional transient problems. So the governing equation would look like c squared times the Laplace of w divided by w of xy is equal to tau prime or double prime of t divided by tau of t. And because we have space on one side and time on the other, we can separate this and make it equal to some omega squared. And we make it negative for the same reasons that we've been stating since we learned this process. We need eigenvalues, eigenvalue functions, or eigenfunctions in the space, and we need, in this case, we're not going to have decay and exponential, but we're going to have an equation in space. The equation is going to look like c squared Laplace of w plus omega squared times w is equal to 0. That looks like a Helmholtz equation again. And in time, we're going to have tau double prime of time plus lambda squared tau of time is equal to 0, not lambda omega. So we go through the same process that we've been going over and over and over, and that would lead to w of x and y equal to the sine of beta and x plus the sine of lambda my. Those are the eigenfunctions in x and eigenfunctions in y. Beta n is equal to n pi over L. Lambda m is equal to m pi over L. And those are the eigenvalues and eigenfunctions because that's case number 9 on the table. Okay? We have first kind boundary conditions on both sides. And the solution for the tau problem, tau of t. Now we don't have an exponential, as you can see. What is the solution to a second order linear ODE that looks like this? Remember? A cosine of omega t plus b sine omega t. And that's why we call that omega omega, because actually those are the frequencies of vibrations of that membrane. Such that omega of nm squared is equal to c squared times beta n squared plus lambda m squared. All right. So now we put it together. Remember that we had let the deformation eta, or the position of the membrane eta, of x, y, and t be equal to w times tau. So this would be a summation from n equal 1 to infinity, summation from m equal 1 to infinity of a and m times the cosine of omega and m t plus b and m times the sine of omega and m t times the eigenfunctions sine of beta n x, sine of lambda m y. And this is a general solution. Okay. So now we have two constants of integration, a and b. But we have two initial conditions. We have the initial displacement and we have the initial velocity, whatever they are. So find a and m and b and m using eta of x, y, and 0 is equal to f of x and y, and the eta dt of x, y, and 0 equals to g of x and y. All right, such that in order to apply the second initial condition, we need the derivative of these. The derivative of eta with respect to time of x, y, and t. What would be the derivative of that big function with respect to time? This will be minus omega and m, a and m times the sine of omega and m t plus omega and m, b and m times the cosine of omega and m t. And then we have the two eigenfunctions, sine of beta and x, sine of lambda m y. So after applying, notice that when time is, we have the two here, the displacement and the time derivative of the displacement. When time is equal to 0, this one goes away. And when time is equal to 0, this one goes away. So we can get a and m from the first initial condition, and we can get b and m from the second initial condition. Therefore, a and m applying orthogonality of eigenfunctions. A and m is equal to 1 over the norm of lambda m, 1 over the norm of beta n, the integral from 0 to L, the integral from 0 to L, f of x and y times the sine of beta and x sine of lambda and y dy dx. And b and m, same thing, 1. Now we have omega and m, 1 over the norm of lambda m, 1 over the norm of beta n, times the integral from 0 to L, times the integral from 0 to L of g of x and y, times the sine of beta and x, sine of lambda m y, dy dx. That's it. Those are the two constants of integration. Remember from the table. We have that. And there we go. So that's it. If for some reason we have non-homogeneous boundary conditions or governing equation, we can apply superposition the same way we did it for diffusion problems, as long as neither the boundary conditions nor the governing equations, non-homogeneities, are time dependent. If one of them is a function of time, we need another technique. We need variation of parameters, we need Green's functions, we need Duhamel's expansion or integration, convolution. Any of those other techniques will get you to the answer, but at the end the answer will look like summations of sines and cosines and so on and so forth. It's just a matter of how we fix those constants of integration. Any questions? Alright, I'll post the homework assignments, but I'll make sure I'll take out all that has to do with variation of parameters. Make sure everything is solvable with the techniques we're going to learn. And starting next week, we'll talk about finite differencing to see if we can find approximations, numerical approximations of these solutions. Alright, have a good weekend.